Okay, thank you for joining me. I want us to look at the wave-particle duality. By this wave-particle duality, it's just an idea that matter can behave as a wave and it can also behave as a particle. Now, we know that matter is anything that has mass and can occupy space. Yes, because they have mass and they can occupy space, they can as well have a wave nature, and then they can as well possess a particle nature. Now, we look at the wave nature of matter. Wave nature of matter. Now, by the wave nature of matter, we want to show that matter can behave as a wave. Now, of course, if it behaves as a wave, it possesses the characteristics of wave. For example, if you have a wave nature, a wave profile like this. Now, by this wave profile has its amplitude, it has its wavelength. It has its wavelength from here. It can have wavelength. So these are some of the attributes of a wave. Now, in order to demonstrate or to prove that yes, that matter have wave ability. Now we can do that using diffraction. We can prove that using diffraction. For example, if we have this as a slit, as a screen, now we can have openings. We can have these openings. Now, if we have these openings here, maybe we can bring light. If we bring out light, shine light here. Of course, these lights will come like this. The moment they come, on getting to this slit, this opening, they can form spherical wavefront here. Now, this one also can form spherical wavefront. By solving, this is our screen. This is our screen. Now, this is a slit or opening. Now, by this opening, this light are coming out here, they diffract. Of course, we know that diffraction is spreading out of waves or passing through a small gap. Now, coming out here, these waves, of course, this is the screen. This screen will collect these light. Remember, these part of these, they will form patches. Some will be, I want to use these as brighter parts, and then, in fact, I will use this as bright parts, use this as dark parts. Now, if we have this as a bright part, bright, dark, dark, dark. Now, this is the nature of this light that will be formed on the screen. Now, this light that is forming on the screen here, two things are happening here. The reason why we have the dark spot here, the dark spot is as a result of interference. If we take a look at this, we'll discover that yes, this light interferes. There is interference here. Now, this interference can be either constructive or it can be destructive interference. That's the two types of interference: constructive or additive. While the other one is destructive or subtractive. Now, the bright portion is caused by constructive interference. They are caused by constructive interference. While a dark region is caused by destructive or subtractive. Remember, this is either you call it constructive here or you call it additive interference. While the dark spot, so I will use this. Why this one is caused by subtractive or destructive interference. Now, why we have these destructive interference, and of course we know that, yes, this destructive interference, that is where we have two or more waves with the same amplitude trying to enter a particular point. Now, as they are forcing themselves, they interfere with each other. So at this point, the product is loud. While for this dark region is where we have this, maybe this wave coming out, we have this, so that they can cancel each other out because they are out of phase, while this one is in phase. Now, this phenomenon will now prove to us that yes, matter can behave as a wave. Now, in general, since we have said that yes, matter can behave as a wave, it possesses the characteristics of wave. Therefore, we cannot define matter in terms of wave by the following wave characteristics. That means we can define it by interference. We have the second one. It can be diffracted, which is what we have here. Diffraction. It can be reflected. It can also be refracted. Or it can be explained by this. And then it can also be explained by polarization. So, in other words, the wave nature of matter can be explained by these characteristics of wave: interference, diffraction, reflection, refraction, and polarization. Now, on the other hand, we want to look at the particle nature of the wave. Now, if we discuss the particle nature of a wave, that means a wave can behave as a particle. A typical example of waves, of matter, please, behaving like a particle is a concept, or using the concept of photoelectric effect. And of course, when we use the concept of photoelectric effect, we can assume maybe we have a sheet of material. If we have a sheet of material, we can incident particle, of course, that this particle is light. If we incident particle on this, because of the photoelectric effect, this particle, hitting this metal surface, it can knock off electron. It can knock electron off from this particle. Now, assuming another particle, we can use maybe two colors. Let's say this one is blue, and then another one is red. Red light and blue light, they don't have the same frequency. And of course, we know that for photoelectric effect to occur, this light coming here, or whatever, of course, this light is light we know is photon. So, if we refer it as a photon, when it strikes a metal surface, it knocks off electron. And the condition for it to knock off electron from this surface is that it must have enough energy. Now, for it to have enough energy, the frequency, so it must have enough energy, and then it must have sufficient frequency. It must have sufficient frequency. Now, these two, one is red, this one is red, this one is blue. Now, red, because blue has enough energy, it has the appropriate frequency. It can knock off electron from this metal surface. Whereas this red does not have enough energy. Because it does not have enough energy, it doesn't have enough frequency. And when it does not have enough frequency, what happens when it shines on this metal surface? When it shines on this when photon shines on this surface, because it doesn't have enough energy and enough frequency, complete absorption takes place. So I will have explained it with blue light that has energy and sufficient energy and sufficient frequency. It can knock off electron from the metal surface, while for red light that does not have enough energy and enough frequency, complete absorption will take place. In other words, matter as a particle exhibits particle nature characteristics, which include, so for particle nature of matter. Now, by particle nature of matter, it can have the following characteristics, which is absorption and emission. Absorption and emission can take place. Photoelectric effects can take place. Compton effects can take place. Thermionic emission can take place. Thermionic emission can take place. So, in other words, we can now, with particle duality, we can now say that yes, it is an idea that says that matter can behave as a wave. If it behaves like a wave, it can be explained with these characteristics here. Now, if it behaves as a particle, it can be explained using these characteristics of a particle: absorption and emission, photoelectric effect, Compton effect, and the thermionic effect. Now, for matter, I'll say, according to de Broglie, we can now say that the wavelength of any particle can be written as lambda is equal to Planck constant all over the momentum. Or we can have that the wavelength of a particle can be expressed using lambda is equal to h all over mv. Where p is the momentum, lambda is the wavelength. Of course, h is the Planck constant. M is the mass of particle. V is the speed or the velocity of the particle. Now, for an electron of mass, ME, according to the Broglie equation, we have that an electron of mass, ME, and accelerating voltage. For an electron of mass, M subscript E, with accelerating voltage V, this equation can now change. If we have electron of mass ME, where ME is the mass of the electron, V is the accelerating voltage. This one now can now change. Lambda can give us here h all over. An electron of mass ME, where MA is the mass of the electron, V is the accelerating voltage. We have this. Or we can see how that lambda is equal to Planck constant all over the square root of 2e v me. Okay, where all these values, all these parameters still retain their meanings. ME is the mass of electron. Please note when ME is given and when M, ordinary M is just mass of the body, but ME, mass of electron. Okay. While this E here is electronic charge, of course it's a constant. Electronic charge is the value of electronic charge E is 1.6 times 10 to the power minus 19 coulomb. That is the value of one electronic charge. Now let us take one or two questions to enable us better understand this. This question on the board here, and this question says, the wavelength of an electron of mass 9.1 times 10 to the power minus 1331 kg, moving with the velocity of this. Now we have the Planck constant there. Now all we need to do is list out the parameters given to us and then we solve. Now we have that the first thing there is calculate the wavelength of an electron of mass. Now mass of the electron is 9.1 times 10 to the power minus 31 kg. Moving with the velocity. Now the V, the velocity is 2 times 10 raised to the power 6 meters per second. Now the Planck constant there is 6.63 times 10 to the power minus 34 joules seconds. Now the formula, as usual, will give us that according to de Broglie, Planck constant wavelength is equal to Planck constant all over mv. In this case now, we have the electron given to us, we can put it here. Even if we put m here, it doesn't change anything. So which will now give us, the Planck constant is 6.63 times 10 raised to the power minus 31, so 34 please, as a Planck constant h. All over mass of electron. Mass of electron given to us 9.1 times 10 to the power minus 31 times the velocity there, the speed, which is 2 times 10 raised to the power 6. Now, which will give us, we'll still write that one, 6.63 times 10 raised to the power minus 34 all over. Now, at this point, we can now multiply. This is 9.1 times 2, and of course, 9.1 times 2 will give us 18.3, 18.4. 9.1 times 2 will give us 18.2, please. Multiplied by 10. Now, we have just multiplied the bases. We cannot add the index number, which is minus 31 plus 6. And it will give us that Planck wavelength is equal to 6.63 times 10 raised to the power minus 34 all over. Now we can have 18.2 times 10 raised to the power minus 31 plus 6 will give us minus 31 plus 6 will give us 20 minus 25 minus 25. At this point, we can send this one up. Remember, if you are dealing with index numbers, please be careful. Send this one up. It will give us 6.63 times 10 raised to the power minus 34. And if this one goes up, it becomes plus 25 all over. I will now have 18.2, which will now give me 6.63 divided by 18.2 will give me 0.364 times 10 raised to the power. I have divided this and this. Now what is left is this. All we need to do is we minus 34 plus 25. And if we add this to this, we'll have minus 9. Therefore, the wavelength will give us, put this in standard form. If you put it in standard form, we'll have 3.64 times 10 raised to the power, sorry, this is 9 here, times 10 raised to the power minus 10 meters. So this is the value of the wavelength of this electron of mass that's moving with this speed. Okay, we have this second question before us. This question says, if electrons are accelerated from rest through a potential difference of 10 kilovolts, and of course 10 kilovolts is 10,000. What is the wavelength of the associated electron? Now, given this value, mass of electron is this, one electronic charge is this, Planck constant is this. Now, the answer, of course, is a JAMB question. The answer was one of these. Now, solution. The first thing we need to do is to bring out these parameters. Of course, the first parameter there is the potential difference, V, which is 10 kilovolts. And this 10 kilovolts is 10 times 1,000, which will give us 10,000 volts. What is the wavelength? That means the wavelength is unknown. We have all these masses there, all these variables. Now, we put our formula, and our formula is Planck constant all over, and of course, the one that has is we have 2 electronic charge, 2 eV times ME, which will now give us that Planck constant is equal to H. We put the value of H to 6.6 times 10 raised to the power minus 34, all over the square root of 2 times 1 electronic charge. 1 electronic charge is 1.6 times 10 raised to the power minus 19, multiplied by V. V is the voltage, the potential difference, which is 10,000 times mass of electron. Mass of 1 electron is 9.1 times 10 raised to the power minus 31. Everything will give us 6.6 times 10 raised to the power minus 34 over. Now we multiply everything out, which will now give us, we multiply the basis, right? 2 times 1.6 multiplied by 10,000 multiplied by 9.1. You can choose to put this in standard form if you want to. That means if you put it in standard form, it will now give you 1 times 10 raised to the power 1, 2, 3, 4. 1 times 10 raised to the power 4. Now, if we make it times 10 raised to the power 4, that means I will have 1 times 10 raised to the power 4 here. Now, if I have it here, I will now have 2 times 1.6 times 1 times 9 points. That. So we now have 2 times 1.6 times 9.1. And it will give us 29.12 multiplied by, you have times 10 raised to the power, I cannot add all this one, minus 19 plus 4 minus 31, which will give us equal to 6.6 times 10 to the power minus 34 over the square root of now 29.12 times 10 raised to the power. I will have minus 19 plus 4 minus 31. At the end of the day, we have raised to the power minus 46. Now, we will now have equal to 6.6 times 10 raised to the power minus 34 all over. Now, the square root of 29.12 times 10 raised to the power minus 46 will give us this. Now, if Okay, when we now take the square root of this, we'll have 5.396 times 10 raised to the power minus 23. Now, at this point, what we will now do is we'll take this value up. We'll take it up, we have 6.6 times 10 raised to the power minus 34. Now, if I take this one off, this minus 23, it will have to give plus 23 all over 5.39. At the end of the day, we now have 6.6 times 10 raised to the power. Now we say minus 34 plus 23 will give us minus 11. Okay, all over 5.39. Now this over this 6.6 divided by 5.39, it will give me that lambda is this over this will give us 1.22 times 10 raised to the power minus 11 meters. And of course, the option is one of the options there. Option B is the answer. So we have this as our option B. Now we have this question on the board. An electron of mass 9.1 times 10 raised to the power minus 31 kg moves with a velocity of this between the cathode and anode of an X-ray tube. Calculate the wavelength of the material. Now we have the Planck constant given to us. Please, if you have followed me through the first and second examples, feel free to solve this. And please give me the answer in the comment section. For more videos, please, if you have not subscribed, subscribe to this channel, share and like this channel. Thank you.